네, 한성민 씨 안녕하세요. 네, 박건우 씨 안녕하세요. 네, 정상국 씨 안녕하세요. 자, okay, so let's start today's lecture. And so before starting today's lecture, I wanted to ask you whether you have done homework number 5 without difficulty. So the homework number 5 was devoted to improve your code to deal with arbitrary structure with multiple regions and multiple contexts. So I wanted to ask whether you have done it correctly or not. So could you please let me know whether you had a problem or not? So okay, great. So then if you are quite good with our homework number 5, then based upon your achievement up to now, I wanted to ask you once again to solve your source free Poisson equation for your structure. So now you can generate an arbitrary structure, and out of them the interface can be automatically recognized, and for this structure now you can solve the source-free Laplace or source-free Poisson equation. Here maybe you can have a certain contact and contact here. So that's all for homework number 6. So you have 5 days 5 days to solve this homework number 6, a relatively long time compared with homework number 5. And I wanted to ask you to sorry about that. I was completely confused with today's today is not Thursday but Tuesday, so you have just 2 days. Sorry about that. So now you have a relatively short time, so please try to implement your code in a short time. So I think that's it for today's lecture. That's it for today's lecture, but I wanted to just to give you some hints. How can you deal with some implementation related issues naturally arisen from this structure. So are you all with me? So you understand the homework number 6. You have generated many structures. Yes, they look quite beautiful. And for them, please try to solve them. Please introduce multiple terminals. Of course, usually multiple means that it is larger than or equal to number 2. But in this case, please try to implement at least 3 terminals. And as I told you before, depending on the excited terminal, please write down in this way. Here you have n or whatever I, but here I means that ith terminal is biased with number 1, and for all other terminals phi is 0. So you understand this one. So for example, if you have 3 different terminals, then you can define phi 1, phi 2, and phi 3. Then please check the sum of phi 1, phi 2, phi 3. Then that will give you certain number. And please compare that number or that function, position dependent function or field, with the one where all terminals are biased with value 1. Then you can find that they means that the sum and this scalar field are identical, so you can find it. Okay, so well, I think that the problem is quite clear, and since we have already discussed about this homework number 6 in the previous lecture, so previously I thought that that is too tight to solve 2 problems, so I just reduced the number of problems from 2 to 1, and now this is the remaining task for you. So now you can try to solve this problem. Okay, so basically the task is quite easy and straightforward, clear. However, in today's lecture, I just wanted to discuss about some implementational details about this problem. Okay. For example, the main difficulty comes from this interface. However, before directly talking about this interface problem, but first of all, let's think about certain case. I mean that here we have oxide, yes, and here we have silicon. Of course, they are attached to each other, but for our conceptual understanding, just to draw them separately. Then, for while right now we are working with just phi function. Later we will call it as electrostatic potential, and you know it has the physical dimension of a bolt, so you know it quite well. But as you all understand, phi, the electrostatic potential, is not the only quantity we have to consider in this semester or computational microelectronics. So there exist two more quantities which are frequently or almost always considered in this field. What are they? Maybe you understand electron density and hole density are those quantities we have to consider. So now think about a general case where you have to solve Poisson equation and electron continuity equation and hole continuity equation for these three quantities. Then what did you do? Okay, first of all, since we have to solve these three solution variables or solve certain equations to get these solution variables, we try to define these scalar fields under regions. So I'll say that okay, here, here, and here we can define electrostatic potential, electron density, and hole density on silicon region. And also in the same way we can define electrostatic potential and electron density and hole density on the oxide region. That sounds great, but you may feel something weird immediately. So could you please show your opinion about what is wrong in this configuration, or what is the points to be improved? So any comments or your opinion? So please let me know. Okay, so let's repeat it. Thank you for your feedback. So our goal is uh, solve the drift diffusion equations. So when I say drift diffusion equations, it is a set of Poisson equation and electron continuity, and also hole, oh no, that here, hole continuity. So the solution of these equations are given as electrostatic potential and electron density and hole density. They are solutions. So my question is, if we have this oxide region and silicon region, oxide and silicon, so in order to solve the drift diffusion equation, I just introduce some unknown variable phi and p in the silicon region, and also introduce phi and p in the oxide region. That looks quite natural, but that is not that natural. So in reality, so I just ask you, what is wrong during my procedure from here to there? So Mr. Han, so now you understand the problem or the question. So could you means that not only Mr. Han, Mr. Jung and Mr. Park, please show your opinion. Mm-hmm. Okay, then how about other students? Not only Mr. Han, so Mr. Jung and Mr. Park, please let me know you have any feeling about weirdness of this procedure. Mm-hmm. Okay. Then how about Mr. Jung? So, okay. Uh, then let's think about this silicon and oxide. And silicon is a semiconductor, and this is oxide is, of course, oxide can be also regarded as a semiconductor material which has very wide band gap. However, usually we treat it as just a perfect insulator. Okay, so are you all agreeing with me? So in this case, for semiconducting material, it is quite natural to define the electron density and hole density. They can be easily found, and we can well define the number. Even in the insulator, if we are talking in a physics-based discussion, then we can find very small number of electron density and very small number of hole density. Mm-hmm. But point is, since we are treating our oxide material as a perfect insulator, so from the beginning of our discussion, we are assuming that there is always zero electron density and zero hole density. There is no charge carrier at all for a perfect insulator. So by accepting that assumption, so now it is quite natural to say the physical or the validity of quantity like oxide electron density in an oxide region or hole density of an oxide region, that their validity is quite questionable. Okay, or we can say in our oxide region, electron density is always zero and hole density is always zero. That is also possible. So yes, we can define in that way. However, the better way is just to, from the nature of the material, so we just neglect them in oxide region. How about your opinion? If we adopt such kind of configuration, unknown variable configuration, now we can say that electrostatic potential is defined on both of semiconducting material and insulating material. On the other hand, in the case of electron density and hole density, they are defined on only semiconducting materials. So, how about your opinion on this configuration? So, I just wanted to ask you, you like it or not? So, could you please show your feeling about this configuration? So, please make a comparison with our, yes, here we have still silicon, the same thing, same reason, and define here electrostatic potential, electron density, hole density, and for these quantities, electron density and hole density in oxide region, actually solving the continuity equations, that is not very convenient. So instead of that, say, instead of solving the electron continuity equation, just to impose these vanishing density conditions for them. So please compare them. So that is so which one will be, okay, so which one will be computationally efficient? So what is the efficiency of these two methods? Mr. Hans told me that means that the left one looks good. And how about other students? So please discuss in terms of the efficiency. Huh. Oh, Mr. Bach, oxide. Even in the oxide, we have to consider electrostatic potential. Otherwise, we cannot, for example, if we don't consider, think about this one. Yes, yes, think about our double gate structure, and here we have fixed potential, and here we have fixed potential. Usually this potential is given as the gate voltage. So gate voltage and gate voltage. Point is, here we have a silicon material and the electron density, which is quite important for our device operation, is determined by the potential here. So surface potential potential is very important to determine the electron density. Of course, not only the surface potential, but potential at this midpoint is also important. But anyway, it is important that the electrostatic potential in silicon region is important to determine the electron density. However, who determines this, or which quantity determines the surface potential or potential inside the silicon region? That is solely determined by this oxide flux. From this gate terminal, we will have a certain electric field or displacement field, and that is screened by our electron gas located here, and eventually all over our electric field is now compensated, screened, and here we have the field which is vanishing exactly. So if we don't consider the electrostatic potential inside the oxide region, then we cannot provide the displacement vector sent from our terminals. So it is impossible for us to consider the electrostatic potential in the silicon region. Of course, the role of electrostatic potential in the oxide region is to estimate the electric field or displacement vector. Okay, Mr. Bob. So now you understand your misconception. And then please comment once again. Here, we have two different ways to define scalar fields like electrostatic potential, electron density, and hole density. I'm now suggesting that a method or a scheme where electron density and hole densities are defined only at some points we need it. Okay. So all other students like Mr. Han, Mr. Jung raised the hands of this left side one. And how about Mr. Park? What is your opinion on these two schemes? So could you please show me your opinion? Okay, yes. So as all of you agree, this one is good from the viewpoint of computational efficiency. So think about this situation. Now you have, for example, 10,000 points for silicon, and for oxide you have smaller number like for example 200 points. So you have 1000 mesh points and 200 mesh points. Then please estimate the number of all unknown variables when we discretize them. Then you can easily understand. So silicon, we have three unknown variables: electrostatic potential, electron density, and hole density, and there are 1000 points. So we will have, yes, 3000 unknown variables for silicon region. And how about the oxide region? There is only one unknown variable, electrostatic potential, and here we have 200. So the number will be 200. Yes, and when we repeat this estimation once again for our right skin, then obviously we will just have the same number for our silicon region, and we will have a larger number like 600. Then the number will be, yes, of course, that is higher. Then when you have a look at the number like this, maybe your feeling will be, yes, somehow we have a certain overhead due to adopting this kind of job. Yes, yes, but the increase is not that high, just to 400. Yes, we can solve it. But you know, your feeling about this one, this number is generated from our relatively small structures. So in realistic structure, the number of grid points is usually orders of 10,000 or sometimes even higher, like 100,000. And of course we have silicon region. However, sometimes we have many surrounding insulator region. So adding them all will make a significant increase in the total number of how can I say, unknown variables. So that is not negligible at all. So please understand this situation. So are you all agree with me? And this is one example, and let me also consider other example. For example, sometimes we have to introduce certain thing like this. Here we have electrostatic potential, electron density, and hole density. But in addition to these fundamental, almost always included unknown variables, also we can introduce further unknown variables in our system. For example, we can think about electron temperature, hole temperature, or also we can think about quantum potential for electrons and quantum potential for holes. So your question can be, is it really common? Yes, in these days, it is really common. Or in practice, you can find many things. So among them, for example, temperature. Yes, temperature can be introduced everywhere. I agree. However, temperature also can be decomposed into three different quantities. For example, temperature of our lattice, temperature for our electron gas, and temperature for our whole gas. Usually, we believe that temperature is a constant and it does not depend on the position. So here or here we have always 300 Kelvin. Or if the temperature is elevated, yes, the elevated temperature is applied to everywhere. That is our simplest setting for temperature variable. However, now if we consider further advanced physical model, then you can find that, now we can define three different temperatures. And in this case, for example, lattice temperature can be a function of position. Then also electron temperature and hole temperature. These quantities are specifying the energetic excitation of our electron gas at certain position and hole gas at certain position. So in general, they can be a function of position. Of course, in the case of lattice temperature, both of silicon and oxide can have lattice temperature. It's good. But how about electron temperature and hole temperature? If there is no electron at all, and if there is no hole at all, is it meaningful to define electron temperature or hole temperature? Nonsense. So, simply speaking, although we are now talking about just electron density, but if we include further and further or additional physical variables are introduced, then sometimes they have correct physical meanings only in semiconductor material. Otherwise, they don't have physical mechanism. Okay, so say 10 P. So sorry about that. I have okay. Then let's come back. Okay, so so electron temperature or hole temperature, those quantities should be defined only in silicon. And what else? Other physical quantity we can think is, for example, trapped electron density. So this is trapped electron density. So it makes further problems. Think about this one. Let's say that this is the region we will consider for silicon material. Okay, now we have a silicon material. Looks like a little bit strange, but anyway, and let's say we have introduced certain traps in somewhere in this silicon material. Of course, in this three-dimensional, in this two-dimensional drawing, so we are always assuming that there exists third hidden dimension here. Okay, so oh, yes, I think that should be yes. Now we think about three-dimensional thing, and yes, so that looks perfect. But let's say that is somewhere here. Yes, there is a certain impurity which is acting as a trap. Trap means that the physical existence which can capture and emit electron. So from the viewpoint of an energetic diagram, then we can say that states over conduction band minimum are called conduction band states, and yes, the states below the valence band maximum are treated as valence band state. However, this trap usually introduces certain energy state around the mid gap. So not exactly in mid gap, but anyway, their energetic position can be located in this forbidden zone, the gap between conduction band and valence band. So now certain electron previously located in this state can emit, for example, phonon and lose its energy and make a transition to this trapped state. So for a while, for some time scale, it can be captured here, and if it takes a certain phonon to get an energy, then it can escape from this one, or even it can move to valence band. Then a hole, previously located hole, is now disappeared. So if this hole is disappeared by movement of this trapped electron, then we say that that happens. The electron hole pair suffer from the recombination process. So now let's just think about this case. Yes, we have only one single position where a trap is existing, and now we have to solve the equations like this. Let's say that this problem is quite important for your application. That is your most important role, let's assume. Then you have to solve Poisson equation. Yes, you can solve Poisson equation. And electron continuity, yes, I can. And hole continuity, yes, that doesn't matter to me. It is quite easy, and everybody can do that. But point is, in the industry, sometimes people want to do additional job. What is the effect of the additional trap introduced at a certain position? Then how can we solve this problem? Of course, then we have to introduce an additional equation for this trap. And for this trap, yes, the balance equation is well known. We can solve it. That doesn't make any difficulty. It looks quite similar with the electron and hole continuity equation. However, there is no spatial deviation. So anyway, it is not that difficult to consider this trap movement. Movement means that the transition of electrons through the trap state. Good, but let's say that for this trap, now we will define the electron density trapped by this trap. So N sub T, trapped electron density. Then natural question is that, how can we define this NT field on our silicon region? Let's say that we have in this time, since the structure is three-dimensional, let's say that we are now spending 10,000 points for our silicon region. Then now we introduce only one single position where trap is existing. Trap is not spread out all over our region, but we wanted to think about the effect of a single trap. Haha. Then if we say, okay, so now let's introduce the electron trapped electron density as a fourth unknown variable, like NT, then we will have just 40,000 unknown variables. Is it really necessary to introduce 10,000 more unknown variables? No. I think that the reasonable way is just to have 30,000 one unknown variables. Only one additional unknown variables out of this single trap is sufficient for our purpose. Okay, how about your opinion on my reasoning for introducing certain scalar variable or scalar field where it has physical meaning? So up to now I have shown you many examples why we have to care about the position. We have to introduce certain unknown variables. If we say that blindlessly, okay, just add them all. So because we have a powerful computer, don't worry about that. We can just solve it. That is not the case for our realistic case. In realistic case, even in the industry, there are so many users for software, the TCAD software, and they are competing to occupy their computing resources. So if we don't provide efficient computer code, then under the given computational resource, the number of available computation job can be reduced significantly. That should be avoided as much as possible. So how about your opinion? So are you all with me up to now? Then if you all agree with me, I can proceed further. So I think that this example is typically interesting to Mr. Park. So it is taken from your research work. So when we try to build a certain code for this trap simulation, so we have to be careful not to introduce our unknown variables everywhere. That is not the case. Okay, students, please respond to my question or leave your opinion. So do you have any question or any comments? Okay, so thank you, Mr. Han. So I assume that there are 10,000 mesh points. So before introducing our trap, so we have 10,000 mesh points, silicon mesh points, and that is given. And yes, we have to introduce 10,000 discretized electrostatic potential in silicon region and 10,000 electron density and 10,000 hole density. So previously we had to introduce that one. However, now we introduce just one single point where we have a trap. But if we just follow the scheme suggested in this right hand side, then okay, just to define any unknown variable to everywhere, then we have to introduce also 10 also 10,000 trapped electron density all over our silicon material. So each one will contribute to 10,000, 10,000, 10,000, and 10,000. So that will give you just 40,000 unknown variables. However, if we just define the unknown variable where the unknown variable has the physical meaning, so still we have 30,000 out of electrostatic potential, electron density, and hole density, and this trapped electron density can contribute only one unknown variable, because yes, there is only one point where electron density is defined. But that's the reason why instead of 40,000, I just told you that 30,001 unknown variables can be introduced by adopting this philosophy. So we have further developed the philosophy. Not only the region-based decision, but even in the silicon region. So when we have a certain physical meaning, only in that case define an unknown variable. Okay, so okay, Mr. Han, you have understood this one. And how about other students? So are you all agree with the efficiency of this left hand side laptop approach? So I think that it is quite much straightforward to understand this approach. Okay, good. And how about Mr. Zhang? So are you with me? So do you agree that we need really to consider the variables only for position we can define certain physical quantity? Okay, great. Then now the point is, think about this one. Good, very good, very good. But point is, it introduced additional difficulty. Okay, it is good for from the viewpoint of numerical efficiency, because we can minimize the size of unknown variable vector. But point is, how can we understand where we have a certain number or not? Let's come back to our simplistic example once again. Now, simplicity means that one-dimensional example. Now, let's say we have I have introduced 7 points. I have introduced 7 points, and yes, the top and bottom point are designated as terminals. So say that this is upper gate and lower gate, or you can say top gate and bottom gate. Yes, and say this is region, 3 regions. And yes, here we have a silicon, here we have oxide, and here we have oxide. Then now let's try to assign our unknown variables. So first of all, let's just consider phi. In the case of Poisson equation only, nonlinear Poisson equation, Laplace equation, yes, currently we are working with that position. So in this case, it's not that difficult to assign unknown variables. Let's say that these points has their own numbers like 1, 2, 3, 4, 5, 6, 7. I just adopted the one-based indexing, but if you are working with other one like a zero-based indexing, then it is always good to use it. So anyway, let's say that we have 7 points and 7 vertex points have their own well-defined numbers. Then you have originally, before introducing the discretization, actually your goal is to find electrostatic potential at a certain position. So certain position can be, for example, even at this midpoint, or point close to somewhere, or exact vertex point. Usually this R can be an arbitrary position vector. However, we don't care about the arbitrary position vector. Instead of that, by discretization, then instead of having arbitrary function or a function of an arbitrary vector, then we will just introduce something like this. So sampled value of phi at R1, R2, and sampled value R6 and R7. So by understanding the 7 numbers which are entries of or components of this vector, 7 by 1 vector, now we say that only understanding this single vector, it is good enough to understand this single vector to have certain information about a function of arbitrary position. Of course, yes, it's not in a rigorous sense. Nobody can say so. For example, let's assume that your signal or your physical quantity actually oscillating in this way. Oh, sorry about that. So at least I have to draw a function. Yes, let's say that this is the exact answer of your problem. Then if we adopt this discretization scheme, then we just select this quantity, and that quantity, and that quantity, that quantity, that quantity, and that quantity. And now you say that with some information for these 7 points, I will reconstruct our solution like this. It changes in this way. Okay, then what is your feeling about that? Somebody can feel that, oh, at least it follows its love structure. looks good, but if we are really rigorous, then it means that we have lost, much information has lost here in this crude discretization. So yes, so you have to understand this limitation of discretization, but anyway, you understand this limitation, and now you just label them as this way. Label them as this way. Yes, phi 1, phi 2, and phi 7, and you treat it as a sampled value. Good, very good. And if you ask me, oh, I have phi 2, or I have the second entry of our unknown variable, then what is it? What is the physical meaning of this quantity? Then now we can say, since it is defined in a position of number 2, it is corresponding to our position 2. And since we are talking about always the electrostatic potential, then electrostatic potential is understood. Yes, that is the way you have done up to now. But now my question is, instead of that, now let's introduce additional variables to be discretized. For example, N, P. Then how can you do that? So if you just adopt our naive approach to define our quantities everywhere, then what you will do is, okay, I need phi 1 up to phi 7, and I need N1 up to 7, and also I need P1 up to 7. You will say so. So then you will need 21 unknown variables, and let's say that you just concatenate them and make a vector whose size is given by 21 by 1, 1. And if we have, for example, second element of this vector, what is it? Since this number is smaller than number 7, it can be treated as phi. And number 2, okay, this is position 2, so we will call it as phi defined at R2. How about your opinion? For example, let's think about 14. 14 is smaller than 14, the second round of number 7. So this is corresponding to electron density, and so 14 is just 7 and 7 and 7th component, so we will have R7. So are you with me? So if we have 16, then this is even larger 14. We feel that this is whole density, and 16 is a sum of 14 and 2. Okay, so that will be position number 2, R2. Let's say that you have followed this way. Then how about your how can you find out the physical meaning of a certain component in your unknown variable? already it becomes quite complicated. But anyway, if you just label them in that way, then maybe you can anyhow, by just considering the total number of your unknown variables, then you can do it in some way. Okay. So if you have any questions, please interrupt me. So, but you know that we have used 21 variables, but you understand actually the number of our unknown variables can be reduced a lot. I mean that phi 1 up to phi 7. And how about electron density? In the case of electron density, N1, N2, no, then we can define N3, N4, N5. And how about hole density? In the case of hole density, P1, P2, that does not exist. So we can say P3, P4, P5. Then how many unknown variables? So we will have 13 unknown variables for this case. So you can understand already we get some efficiency by adopting our strategy to define some quantities where we need that quantity. Sounds good? However, now you have some difficulties. So how can you find the physical meaning of your second variable? Second entry of your unknown vector. So in this case, that is smaller than 7. Yes, maybe you can try to that. However, if we say number for example 9, then what is it? Can you easily understand this is corresponding to your N4? Or if you have number 12, can you easily understand this is corresponding to your P4 quantity? So you feel that it is really difficult to find out physical meaning of your unknown variables. So you need some ways to encode your unknown variable vector. Okay, so are you all with me? So up to now, I have shown you that in order to have certain efficient implementation to reduce the size of an unknown variable vector, we have to consider how can we assign our defined unknown quantities into unknown variable vector. So that is not a trivial job. So you have to consider them seriously. Okay. Of course, in order to solve your homework right now, you don't have to worry about that. Instead of that, you have to worry about this one. Okay, so for why in solving today's homework problem, you don't have to worry about this kind of problem. Just to use because we have only one single unknown variable like a phi, and phi can be defined each vertex, and just to consider the material then you can, at least you can calculate the source-free Poisson equation easily. However, in this lecture itself, we are now talking about the beyond that problem. If we have to consider multivariable problem, then we have to define somewhere the position inside the unknown variable vector. Okay, so I wanted to wrap up today's lecture because if we go further, then maybe it can interrupt the discussion from now on, can interrupt your solution procedure for homework number 5. So for a while, just to neglect today's lecture contents and just to solve source-free Poisson equation. That is not that difficult. Just to define everywhere, every vertex, the only phi, and depending on the vertex number, vertex index, just to construct an unknown variable vector, then solve it. It is not that difficult. However, after you successfully do the homework number 6, then we will consider more general cases. So please be prepared in your mind. So later we will discuss about how can we place our unknown variables in our unknown vector. Okay, so how about our students? So you have, uh, please leave your message whether you have any question on today's lecture contents. So that is not that much related with today's lecture solution, because today's lecture today's homework problem can be solved without understanding all kinds of discussion up to now. But please give your comments or feedback on today's lecture contents. Do you have any question? So if you don't have any further question, I can wrap up today's lecture. So I'm waiting for your feedback. Okay, Mr. Jung, thank you. Okay, Mr. Park, good. So it is always good to give a question. Okay. Okay. So whenever you have additional question, please let me know. I will try to answer to your question. Okay. Then thank you for your active participation today, and see you this Thursday. And although you have just a short time to solve your problems, but solving the solving the source-free Poisson equation for that problem is not that difficult, I hope. So you can immediately solve it. So see you Thursday. Bye.